All right, hey you guys. A lot of people were out this week, and we started a lesson on optimization. We're gonna have a quiz on it next week. So I wanted to go over some of the problems that we already did in class. But let me start with the one that you guys haven't seen, even if you were in class. And that one is from the homework. So go past the first four that were on a worksheet and take out the homework. And on the homework, I don't really care about one because we already went over it. And two is similar to also. Three is also similar to one we've done. No, just kidding. Three is different. Three starts talking about surface area, so three is different. And this is the one I wanted to talk about. So I'm going to start here, and then I'm going to backtrack to the ones that you missed if you missed class on Monday, Tuesday, or the day before, Friday. So let's get going. So starting with three, it says a manufacturer wants to design an open box having a square base and a surface area of 108 square inches. What dimensions will produce a box with maximum volume? So let's think this through. We need a box, and that box has to have a base that is square. Whoops. Not the best start. All right, so the box has to have a base that's square. So picture a box. This is a square. What's it mean for this to be square? It means if we're talking about length times width times height, then the length and width have to be the same because we're a square, right? So I wouldn't even call it length and width. I'd just call it base and base because they have to be the same thing. So if you wanted to use length, width, height, you could, but you'd have to use like L and L, length and length, to show they're the same, or width and width, whatever. But basically, we're supposed to figure out the best dimensions. So do we want to be kind of short, like this? Or do we want to be big and tall? We don't know. We'd have to do the math and figure it out. But also we're open topped, so you can kind of see that back corner there. So you got four walls and a floor, but no ceiling. Okay, that's kind of what's happening here. So we have to label this, and like I said, I'm going to let the base be B for base, and then the other dimension is also B for base, because we have to be a square. And then the height, I'll let that be capital H. And there's all my dimensions defined. So in terms of what equation am I trying to optimize? We're trying to optimize volume. And since volume, you probably know it as length times width times height. Actually, that would be lowercase h for the formula. But for us, our volume is going to be a b times a height. So our volume formula is pretty easy. It's actually just going to be b squared times h. Now there's a problem with this, of course, and the problem is that volume is being defined in terms of two variables, base and height. We still really can't have that. We need to have one variable only. So what we need is a constraint equation, and that's where this information about the surface area being 108 square inches comes in, because surface area is always going to be the sum of the areas of all faces. Okay, now normally with a box, you're probably thinking of like a cube. So like if you were rolling a pair of die, then of course you know there's 1, 2, 1, 2, 3, 4, 5, 6. There's 6 faces. But they said an open topped box, right? So there's no top. So for this box of ours, there's only 5 faces, and those faces are the square on the bottom, plus a rectangular wall, a rectangular wall, a rectangular wall, and a rectangular wall. And my square base is b by b, so that'll be b squared. And all of these faces are b by h. And there's 4 of them, and all of them are b by h. So they all have areas of base times height. And since there's 4 of them, we can just multiply by 4. So there's our surface area formula, and we know that has to equal 108. So, since the formula that I'm trying to optimize up here has base and height in it, we would want to solve this surface area expression, either solve it for B or solve it for H. And we really can't solve it for B because there's a b and there's a b that's squared. So trying to isolate b would not work out great for us. So solving for h is going to be much easier, because to solve for h, you'll just subtract b squared from both sides. So you'll have 108 minus the b squared. Then to get h alone, you would divide by 4b. And the next thing you know, you got a formula for h that came straight from our constraint equation, and we can now bring that up and substitute it into our volume equation. So we've got b squared now, and now instead of h, we'll substitute in this expression, the 108 minus b squared over 4b. So this now seems way worse, right? It seems like we took a very clean expression and made it nasty, but it's better for it to be ugly like this, but to only contain one variable, than it is for it to be clean and have two variables. You just got to trust me on that. So now what? Well, let's take this ugly expression now and clean it up. And I'd clean it up by taking the b squared and distributing it in. And then also, since I'm dividing by 4b, I can just divide each term. So we could just do the 108 divided by the 4b, then do the b squared divided by the 4b, and just turn our equation into two kind of clean terms. So what's this going to be? It's going to be 108 times a b squared, but divided by 4b. And then we're subtracting from that b squared times b squared, which is b to the fourth, but divided by 4b. And then this cleans up. We can cancel 1b with one of the b's from the b squared, so we just have 1b left. And 108 divided by 4, we can just do that math. That comes out to 27. So we now have a volume that equals just 27b. And this guy simplifies too. The b will kill one of the b's, leaving us with a b cubed. And instead of dividing by 4, I'd express that as just a b cubed that has a coefficient of 1/4. And finally now, we've got a not that bad looking equation for volume. So we'll go ahead and differentiate that, because if we're trying to maximize volume, we know that the maximum will occur when the derivative is 0. So this unit on optimization is still really just boils down to finding the derivative, setting it equal to 0, and solving. So my derivative of 27b is just 27. My derivative here would be 3 times 1/4, so 3/4, times b to the 3 minus 1, so down to 2. But that's it. That's my derivative, and I'll set it equal to 0, and I'll go to solve. And to solve, I'll add the 3/4 to both sides. So we get 27 equals 3/4, well, 3/4 b squared, I meant. We're going to add the whole thing to both sides. And I'm starting to run out of space. That's fine. Okay. So now what? You would want to get rid of this coefficient, and the easiest way to do that is probably to multiply by the reciprocal, 4/3, and you'll do that on both sides. Ugh. 4/3. Okay, so the 3/4, 4/3 cancel. Right hand side is now just b squared. Over here on the left, you can multiply by 4, then divide by 3, or you can divide by 3, then multiply by 4, and that's a little easier because 27 divided by 3 is 9. 9 times 4 is 36. Now we just take the square root. And again, technically, when we solve by taking the square root, we get both a -6 and a +6. But remember, for the context of this problem, we're trying to build an open box, remember? So I'm pretty sure that the length of the base of this box can't be -6 inches. That doesn't make any sense. So because of the context of this problem, negative answers don't necessarily make sense. Now, don't start thinking that you can never have a negative answer in a problem, because of course you can. There's plenty of things that are actually negative, like you could make a negative profit in a business if you're losing money. If you're trying to find the best temperature to store frozen foods, that might be a negative temperature. So don't start throwing negative numbers away just because. think about what the question's actually about. But for most geometric problems, it's not okay to have a negative number. Although, if we were doing a problem about a unit circle or something, then you know there is such a thing as a negative angle. Negative angle just rotates clockwise instead of counterclockwise. So there's always settings where maybe a negative does make sense. This one doesn't, so throw it out. It's extraneous. And again, we're not quite done because we may have just figured out that the box of maximum volume has a base that is 6 by 6, but we still don't know the height. But luckily, all you gotta do is look up a little bit. Didn't we take our constraint formula and literally turn it into an expression that was equal to h? So that's how we'll find h, is we'll just grab that same expression that we came up with from our constraint equation and we'll substitute into it. So we know the height is going to be whatever 108 minus 6 squared divided by 4 times 6 is. And so that's 108 minus 36 divided by 24, which is 72 divided by 24, which is 3. So we know that our little box will have the maximum possible volume if we let it be 6 inches by 6 inches by 3 inches. So that's it. That's how you do these problems. If you're kind of seeing these optimization problems for the first time because you were absent, then remember that what we did was we tried to write an equation to model the thing that we're actually optimizing, which in this case was volume, and optimizing it meant finding the maximum. Then there's pretty much always some kind of constraint equation that you have to use, and typically you're using it to eliminate some variable. So we started out with a length and a width and a height, and then the fact that we knew the base was a square meant that we could eliminate one variable because length and width had to be the same thing, had to be b and b. But we still had some h, and so to get rid of h we had to solve the constraint equation to find some expression that we could substitute in, replacing h with an expression containing only b. So then we could take that, boil it down, simplify it, take the derivative, go from there. So hopefully that made some sense to you. I'll scroll back down to the final answer. But the final answer, don't forget, the final answer was never that the base was 6, right? The final answer was giving me all the dimensions of the box. And technically there's another question I could ask too. So I might actually ask, well, what's the volume? So you might want to tell me that the dimensions are 6 inches by 6 inches by 3 inches. And that of course means that the volume is just 6 times 6 times 3, which is like 108. I think it's 108. And that would of course be cubic inches. So don't forget to keep your units straight. When you're talking about volume, make sure you use your cubic units. When you're talking about the sides of the box, talk about plain old inches. But that's it. 13 minutes, that's not so bad. Anyway, if you're watching this now because you're in period 6 and I'm not there to do it with you because I'm proctoring, then that should be it. You can kind of tune away and do some more homework. What I'm going to do now is go back and talk about the ones from Monday, Tuesday. Okay, so if you weren't here Monday, we started by going over this problem here. And this one I hope kind of keeps it simple, so we'll start here. It says find two numbers whose sum is 30 and whose product is as large as possible. So product is what you get when you take two numbers and multiply them, right? So the product of our two numbers, well, what would that be? Well, first you need variables. You could use x and y. You can use a and b. I don't care. I'm going to use a and b for a change of pace, but our product would be a times b, and that's the thing we're trying to actually maximize. So that's the thing that would actually have to do the derivative of and try to find the zeros of our derivative. But again, this is more than one variable. So how do I get that variable count down? Well, we had this constraint that said the sum had to be 30. So if the sum of my two numbers is a plus b, then we know that a plus b must equal 30. And for this problem, you can solve for whichever variable you want. Obviously, solving for a just means subtracting b, and solving for b just means subtracting a. There's literally no difference in which one you solve for. It doesn't matter. So I'll just subtract, I don't know, a to get an expression for b. That means I can now head back to the equation I'm trying to optimize. And now my product is equal to a times not b, but the thing we just solved for. So b is 30 minus a. So instead of b, I can write 30 minus a. Now I have p defined in terms of only one variable. And I can distribute this a to get 30a minus a squared, which is a very easy to differentiate equation. So I'll differentiate it, and we get a p prime that equals 30 minus 2a. And I know that the only max or min of this original function has to occur when this derivative is 0. So I'll add 2 to both sides, 2a of course, and I'll divide by 2. And that tells me that one of the numbers is 15. Now how do you find the other number? Oh right, you just head back to your constraint equation, which very handily says that 30 minus a will give you b. And we just figured out that a is 15. So 30 minus 15 is 15. So we did it. We figured out that the two numbers that add up to 30 and that have a maximum product are the numbers 15 and 15. And therefore, if I asked you to find what the maximum product was, well, 15 times 15 is 225. So you could tell me that the two numbers that maximize our product are 15 and 15, and our maximum product that we could get is 225. So that's that. All right, another one that we did in class was this one, about trying to find the minimum possible point from the graph of y equals the square root of x to the 0.50. So the 0.50 is that guy right there in red. So let's imagine some points on the graph. Let's put a point at 1, 1. Let's put a point at 4, 2. And then let's just put a point at 6, comma, whatever the square root of 6 is. But looking at this, you can see that the distance from 1, 1 to this point, pretty long. Distance from 5 to 4, 2, well, that's pretty short. That's might actually be the shortest. And then the distance from 5 to this point is actually getting kind of longer again. So if these 2 points were called A, B, and C, then hopefully you can tell that what they're talking about here is A is obviously pretty darn far away from the red point. B is pretty close though. C is getting further away. So we know that the right answer is probably somewhere around here. We're trying to find that minimum distance. So how do you actually do that? How do you turn that into like a math expression that we can actually differentiate and solve? Well, there is a formula for distance, right? Isn't it just called the distance formula? So you may have forgotten how the distance formula works, but I'll remind you. So the distance formula says, it's this big old square root. Distance formula says distance equals the big old square root of the x coordinates of the 2 points subtracted and squared plus the y coordinates subtracted and squared. So if that's the distance formula, well, then we need to let one of these points be, well, I guess it just has to be x, y, right? We don't know the coordinates, so let it be variables, x comma y. And then we can substitute in to the distance formula and say, if I want the distance from the point xy to the red point, which is 5, 0, then the x's will be x minus 5, and we'll square that. And the y values will be y minus 0. And so that, if you start to clean that up, that'll be the derivative of, I forget now, do I want to bother expanding this out? I don't remember. I guess I do. Do I? Maybe I don't. I'm going to leave it alone. So it's x minus 5. And the other one is plus y squared. Oops, that one's squared too, of course. And it's all under one big radical. And again, I'm sure you're noticing that we've got x and y. And again, we really can just never have more than one variable. Not going to work for us. So what's our constraint equation? Well, you may not sort of process this, but hopefully you do. For a point to even be on this graph, right, it has to obey the rule of the graph, which is the fact that y has to equal the square root of x. That's literally our constraint equation. So we're kind of constrained by the fact that, well, we can't use this point. We can't use the point 4, 1, because 1 is not the square root of 4, right? Only 4, 2 actually falls on the line. And this is the relationship that dictates that, right? Is that the y coordinate has to be the square root of the x. So that means I can literally take this y and replace it with the root x. And then I'll only have x's. And let's see what that looks like. We'll have our x minus 5 all squared. Then instead of this y squared, we'll have a root x that we can square. So it's not even going to stay a radical very long because we can square that radical, get something else. And I guess that's telling me I do want to expand this out. So if I expand this, then we're now looking at d equals an x squared minus 10x's plus 25 and then plus 1 extra x. And all that is still under the radical, which means d is equal to an x squared minus only 9x's plus a 25, and all of that, instead of a radical, I'm going to call that to the power of 1/2. So now we can differentiate, and we'll get ourselves a d prime that equals, well, let's see, we multiply by 1/2, so that gives us a coefficient of 1/2. We leave this inner function alone, x squared minus 9x plus 25. Then we subtract 1 from our power, so that goes down to negative 1/2. Then we chain rule out the derivative of the inside, which is a 2x minus 9. All right, that's our derivative. Not very good looking, but that's okay. I would rewrite this. We'll still call it d prime. Now I've got a negative exponent, so I know that I'm going to want to make a fraction and push all this stuff that's being raised to the negative power, push it down to the denominator. So you got this x squared minus 9x plus 25. That's in the denominator now, and we'll make it back to a radical. Then this 1/2 would be a 1 in the numerator and a 2 in the denominator. So the denominator is actually 2 times this square root. And then in the numerator, we just have our 2x minus 9. So that's our derivative. And if we want to maximize something, we would want to find the zeros of that derivative. If we want to minimize something, we'd still want to find the zeros of that derivative. Either way we go, we want the zeros. And by the way, this is minimize, right? We're trying to be closest to this point. So we want this distance to be at a minimum. So what do? I guess I set the whole thing equal to 0 and I try to solve. And the good news is, to solve this, we know we can just kind of take the numerator and set it equal to 0 separately. And solving this is cake. It's, add 9, divide by 2, so we get 9/2, aka 4.5, but we're going to call it 9/2. Now, there are other critical points, right? And those are technically the ones I get when I take my denominator and set that equal to 0, because then that's a point where my derivative would not exist. But if I grab this whole thing, the 2, the square root of x squared minus 9x plus 25, if we set that equal to 0, we would divide by 2 and the 0 wouldn't change. We'd square both sides and the 0 wouldn't change. And then we'd have this quadratic. Now this quadratic is not factorable, which means you'd have to use negative b plus or minus the square root of b squared minus 4ac all over 2a. Remember, that's supposed to be a 4. It just gets connected by my program. All right, if you were to use quadratic formula to try to find any zeros of our denominator, you'll pretty quickly find that all this stuff under the radical, which is called the discriminant, this number is called the discriminant. But if you do b squared, that's negative 9 squared, minus 4 times a times c, well, this is going to be a positive 81 minus a 100. That's negative 19. And I can't help but think that if I'm taking the square root of negative 19, then the only answers I'm getting are going to be non-real. So that's good work. That's good work thinking about if our derivative would ever be undefined. Let me move my face. This is the work I was showing over here. But that denominator isn't going to deliver us any new solutions. So that means our only solution to consider is the one we got from the numerator, which says that x would be 9/2. And so that's it. That's the right answer. Now, one thing I've been kind of shirking my duties on is, technically, I don't really know that 9/2 is minimizing my distance. It could be maximizing, right? We've talked about this for a while. But if all we know is that we've got some function, and if 9/2 comes out as a maximum or a min, I don't really know if 9/2 is at this maximum or if 9/2 is at this minimum. So technically we should be testing still and doing our first derivative test. So if we take 9/2 and plop it down in the middle, and if we consider a number less than that, we'll go to your first derivative. This numerator would be negative for numbers less than 9/2. My denominator would be, well, I don't know. If I plugged in 9/2, I think I would get a positive, wouldn't I? And then the square root of that positive would be a positive, and then times 2 would be a positive. So a negative divided by a positive is making me negative. Then my numerator, if I'm greater than 9/2, the numerator will switch to positive. The denominator is just going to stay positive, and that makes us positive. So if you had to justify why 9/2 was a min, you've got your first derivative test now to justify that we went from decreasing to increasing, and that's why the critical value that we found must be a min. And so that's great, that's all well and good, but you're supposed to be giving me a point. So the x coordinate is 9/2, but what's the y coordinate? And to find the y coordinate, as always, just go back to your constraint equation, because we know that y has to be the square root of x. So it's the square root of 9/2, which means it's the square root of 9 divided by the square root of 2. You can just separate those. Then that's plain old 3 divided by the square root of 2, which, if we clean up the denominator, which I strongly recommend you do, then we get our y value, which is 3 times the square root of 2 divided by normal 2. So that means our final answer here is the ordered pair. It's the point 9/2 and then 3 root 2 over 2. That is the point that would be at the minimal distance. And by the way, if you take that point and go back to the graph, 9 over 2 is just 4.5. So if we draw the point that's at 4.5 and go straight up, you can probably agree that that distance right there is actually a little bit smaller than the orange distance. And as soon as I tried to move away from that point, we'd be right back to getting a little bit longer distance again. So I feel really good that that point right there truly is the point that is the very closest to 5,0. Okay, so that's how these optimization problems feel. I do think we did one more. So if you're still with me, we'll do one more. But this one is again talking about an open top box, but it's not like the surface area problem that I did at the beginning. This problem is instead talking about how you could take a regular sheet of paper, or in this case, metal? Oh, a piece of cardboard, sure. But anyway, this piece of cardboard is 14 inches by 30 inches. So it's a pretty long piece of paper. And what their plan is to cut out a square from this corner, cut out the same size square from that corner, cut out this one, cut out this one. And then what they're going to do is fold along these lines. Fold, 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 and fold. And what that should do is it should make them a shallow little box. So remember the square that they cut out? They should end up with a box that's as tall as that square. Then whatever this dimension is, that becomes one of the walls. And then this dimension right here would become the other wall, pushing back into the screen. And then we kind of close it up. And then again, this would be open topped again, because the way we cut the paper and folded, we're going to get this sort of dished out pan thing, like a brownie pan, kind of the dimensions of a brownie pan. Anyway, what's important here? What's important is this whole dimension might have been 14, but then we cut two squares out of it. And these squares are the whole point of the problem, is we're wondering how big should those squares be so that this brownie pan has maximum volume. So we need a variable. We would need to let the size of the square be something. And x by x makes sense to me. Now there's another square up here. That's x by x. So what's this dimension here? Well, if the paper started out, or if the cardboard started out 14 inches long, then that dimension now, which is this dimension right here, by the way, that dimension is now going to be 14 take away 2 x's. 14 minus 2x. And the same thing is going to happen on the 30-inch side. Again, we're going to take away 2 x's because there's another square over here that's x by x. So this dimension we care about is going to be 30 take away 2 x's. That's that. And we already said that whatever the side of the square was, that dimension translates to be the height of the box, which would just be plain old x. So we've got everything now. We know that volume is length times width times height. So for this particular problem, we don't really have a constraint equation. The constraint equation is just kind of the dimensions we were given. But instead of a constraint equation, we still ended up with only the one variable, and we know that length is going to turn into 30 minus 2x. And our width will turn into 14 minus 2x. And for our height, we'll still have sort of this straggling old just x value. All right, so this is the equation I want to maximize. So if I want to have any hope of differentiating v, I should probably expand this out rather than trying to do some triple chain rule thing. So I would take the first two terms first. And you're just foiling. You just foil this. So v is going to be 30 times 14, which is 420. Then it's going to be 30 times 2, so negative 60 x's. Then the middle terms are giving negative 28 x's. And then negative 2x times negative 2x will be positive 4x squared. And then don't forget, you still have another factor of x that would be distributed onto this whole thing. So two birds, one stone. Let's reorganize. 4x squared is going to become 4x cubed, and that's going to come first. Then these middle terms, this is what, 88x? So times another x will be minus 88x squared. And then we've got the 420, which will become plus 420x. And again, if we're trying to maximize this, then our job would be to set this equal to 0. And, oops, nope, just kidding. We have to differentiate first. So let's find v prime. And v prime will be 12x squared minus 176x plus 420. And you may be asking yourself, how can I possibly factor this? And you're right, the way the numbers are right now, it'd be very hard to factor. But you, I hope, are recognizing that, like I already said, we're setting this equal to 0. And that means we can divide through by the greatest common divisor. And I can obviously divide them both, but all three of them by 2. I can divide by not 6, I think 4. I think 4 is the best we can do. So if I divide by 4, I get 3x squared minus, this goes in 44 times. Feels right to me. All right, and then 4 goes into the 420 105 times. So this is still kind of a bad equation to try to have to factor, but let's do it anyway, because we know that we'll take our A value, which is 3, multiply it by our C value, which is 105, which means we're looking for factors of 315, and we're looking for factors that add up to negative 44. So the only thing that jumps out at me, well, I mean, I guess the 3 and the 105 jump out, but that's definitely not adding up to give 44. Then 5. 5 divides anything that ends in 5. So 5 goes into this 63 times, which is still not giving 44. So here's kind of a neat trick. Now that these numbers are smaller, think about 63. You know 63 is just a 9 times a 7. So grab the 9. Let 9 be the factor. And then the other factors are 5 and 7, so put them back together, you got 35. Now you know that 9 times 35 would make 315, and you also can see that it adds up to 44. So that's the right pair of factors. Now to get negative 44, we would need both of these numbers to be negative. So negative 9 and negative 35 are the factors that will allow me to break this guy down. So what are we getting? I still like guess and check, so I know the only way to get a 3x squared is with a 3x and an x. Then I know I'm trying to get a 9 and a 35. Now since I already have a factor of 3, I'll just put another 3 here. Then my outer product will be a 9. Then my inner product wants to be a 35, and I only have a 1, so I'll have to put a 35 here. And they both should be negative. They both are minus, right? But that's it. If you FOIL this out, you'll find you get back the same bright blue equation right above it. So that's it. Now solving these gives me what? If I set this first factor equal to 0, I add 35 and I divide by 3. So x equals 35 thirds is one possible value. And the other value is just x equals 3. So there's two possible answers here. Or are there? Because I can't help but think that 35 over 3 is just a little bit less than 12. But don't forget what the heck we're doing here, right? We're trying to make a little brownie pan thing. And if one of the squares I'm trying to cut out has sides of like 12-ish, don't forget the size of the paper that we started with was only 14. So you can't cut out a big honkin' 12-inch square and then another big old 12-inch square. There'd be no paper left, right? So we kind of have this natural domain that says, hey, these squares, they can't be any bigger than 7 because our shortest dimension is 14. So half of that says 7. In fact, you can't even have 7. The length of the square would have to be strictly less than 7, right? There's got to be actually something left. Anyway, I guess that means that despite our perfectly flawless algebra, we've landed on an answer that's actually extraneous. And it's not extraneous because it's negative. It's actually extraneous because it's too big. But that means the only other answer is 3. And again, technically I should be running a sign test to make sure it's actually a maximum. But if you plop down 3 and then test your factors, then to the left of 3, like at 0, we're getting a negative, and we're getting a negative, so that's positive. And to the right of 3, like at 10, that's still not big enough. Oh, right, because we're ignoring the 12. That's fine. The 12-ish, I mean. So be careful, because there's technically another place out here where our derivative changes again. So you actually can't do that thing I sometimes do where I just imagine plugging in a million. You better plug in a number that's somewhere between 3 and 12-ish, because we need to be right on the other side of 3. So let's just plug in 4. And 4 ain't doing it, we're still negative. 4 here is doing it, so we switch to positive. So we do get a negative. So that means since the derivative on either side of 3 goes from positive to negative, that means the function goes from increasing to decreasing. And that proves that the extrema that we get at 3 really is a max. So what's the answer to the question? What the heck were we actually doing again? Technically we were just solving for the lengths of the sides of the square that we should cut out. And so those squares are going to be 3 by 3 squares. but maybe more interestingly, what are the actual dimensions of the box, right? Well, the height is obviously 3 because it's just x. The width here would be 14 minus 2 times 3, so 14 minus 6, which is 8. And 30 take away 6 is 24. So if I asked you, instead of just finding the side of the square, if I asked you to find the length of all the sides of the box, you'd tell me that is it inches again? It is. So you'd tell me that a 24 inch by 8 inch by 3 inch box, that's the box that will have the most possible volume. And of course we would get that box by cutting out a square whose sides are 3 inches. So that's it. That's the whole problem. And so this is optimization in a nutshell. Are there any problems that we haven't gone over at all? The answer is yes. If you look at the first sheet, I mean, number 4 we didn't do. It talks about 2 towers that have some distance between them. So there's a tower over here, then there's a taller tower over here, and they're some distance away from each other. And what you want to do is support the both of them with a wire, and that wire runs down to somewhere on the ground. Maybe it's right there. And this wire runs up to somewhere on the ground there. And you want to use the least amount of wire possible. So basically you've got wire 1 and wire 2, and you want to keep wire 1 plus wire 2. You want to minimize that. So you could just call that W for wire. So wire equals wire 1 plus wire 2. Now how do you find wire 1? Well, this is a right triangle after all. So this would be some big old Pythagorean theorem problem that ends up with wire 1 being equal to the square root of some junk squared plus some other junk squared. So we end up with a radical plus another radical, which is kind of no picnic to try to differentiate, and it's definitely no picnic to try to solve by hand. So I'm not super concerned about these problems that talk about the towers. But you should go through them. Like, you should definitely know how to do them. But the chances that I put them on a quiz are slim. What else? I don't know. I'm not going to talk anymore. We're up 42 minutes now, so I don't know that anyone's watching anymore. But do as much of the homework as you can at this point. At this point, we should have spent a night doing odds. You should have spent a night doing evens. You should have tried them all. And then just hit me up with questions in class. I will see you guys Monday again for sure, and we'll review. Then there's no school Tuesday, so I am thinking this quiz is probably Wednesday. So if you don't do some work, you may come in Monday, review day, feeling completely lost, and then you can't get help Tuesday, and then Wednesday you're going to have a bad time. So do work as soon as you can, and come to me with intelligent questions as soon as you can. All right, thanks. I hope you guys have a good weekend. I hope your AP week was not so bad, but I'll see you all soon. Bye.